Well, in this scenario, we are only going to slip at one place instead of all places possible. And that's always kind of curious because which one is going to slip and where is it going to slip at? So consider what's going on here. We have a beam that doesn't have any weight, but it's got a triangle load on it. This is a friction point there and a friction point there. We're going to pull on this with a force, and it's going to slip someplace. It's either going to slip at C or it's going to slip at B, and we have to determine where it's going to slip. We have some, this beam is weightless, but it has a force. This beam actually has a mass of 50 kilograms, and we have some coefficients of friction at each of our points. So let's draw a free body diagram of the horizontal beam and see what we can come up with. All right, so I have a AY and a BY and a resultant of that distributed force. And I'm going to put a X in here, and I'll show you why in a minute, but there's going to be X and an AX. All right, let's talk about that resultant force. It is triangle load, so that's going to be 1/2 BH. The base here is 2, and the height is 800, so that's equal to 800 newtons. If I sum the moments about A equals 0, I should be able to find out what B is, or By is. So I'll say minus the resultant is 800. Lever arm is 2/3 of 2, so that is 4/3, plus By times 2 is equal to 0. So By is equal to 533 newtons. Now let's move to the vertical post, because that's where the action is. If I draw a free body diagram of that, you should be able to see what's going on. I have a By. And move that up just a little bit. And I have an CY. Now I'm going to pull here with a pulling force. Now, as you pull this thing, you should expect that some movement might occur, but it's going to be resisted by some friction. So I'm going to put a CX over here and a BX right there. Now, those CX and BX are going to be mu normal once we decide to apply that. But I don't know which one it's going to slip at first, so I have to assume a direction. So I'm going to assume, number one, that it sticks at C and slips at B. All right, so we're just going to analyze that one first. Let's look at this pulling force. It has two components. There's going to be a component in this direction, is the 4/5 P, and a component in this direction, it'll be the 3/5 of P. And I forgot, there's also a weight, an mg. So we'll get to that one in a little bit. Okay, let's sum the moments about C, C, and see what we find. Sum of the moments about C is equal to 0. So here, if it slips at B, Bx is mu normal, which would be mu B. That's going in the positive direction. So it'll be mu By, and the lever arm here is 0.7. And what's pulling it would be the 4/5 component of P, and that's got a lever arm of 0.3. Now I know By, I don't know P, I know that mu, and I can solve that then for P here to slip is going to be 622 newtons. All right, so there's my first force. Second scenario is that it sticks at B and slips at C. All right, well, let's try a moment equation again and see what we get. So let me move that up just a little bit. Maybe I'll zoom out a little bit. There we go. Okay, let's do the moment equation about point B this time. All right, in this case about point B, I have minus CX. And if it slips at C, that's going to be mu C. And its lever arm is 0.7 plus 4/5 of P, and the lever arm of that would be 0.4 equals 0. Now I could solve for that if I knew what C was, but I don't. So we have to do another equation. In order to find out what the lever or what the force at Cy is, I have to do sum of the forces in the y is equal to 0. So in that case, I have minus By minus mg plus 3/5 of p plus Cy is equal to 0. And I'm just going to give you the answer here. I have By, I've already solved for that. I've got mg of 50 kilograms times 9.81. I don't know P, but I can write C as a function of P. And I can plug it into this equation, multiply it by the coefficient of friction, and that is 0.2 down there, and then solve that for P is equal to 354.8 newtons. Okay, so then you compare the answers. Which one happens first? What is most likely to happen? Well, clearly, this is the lower amount, so that's going to happen before this one does. So we declare that this one is the winner, and that's what happens. It slips at C first. All right, this next problem is actually in your textbook. This is an example problem, but it is really key to to this type of analysis where you go from one joint to another or one portion of the slipping scenario to another. In this case, what we have is two blocks, and they're connected by two force members. Those are just rods with two force members, and you're going to be pushing here. There's friction at both places. And what you want to do is find out where's it going to slip first. So a good way to approach that is to consider this with just the method of joints, which I've done. And then you get that as a function of P in both cases. You don't know what the absolute number is, but you do know it's a function of or a fraction of P. Then taking that fraction of P, you can push it down here and say, all right, now I just have this pushing situation for this one. And I can find out what P it takes to make this one slip, which you've done. Again, you can walk through the arithmetic and make sure that you understand it. Takes 31.8, value of this P will slip at, a value of 31.8 here will make this one slip. Now let's move over to this one here. We have a BC over here, which we have as a function of P. We plug that in here, and we find out the slip force here is 45.87. So in this case, it takes more P here to make this one slip than it does this one. So this one turns out to have the slip first condition.